Now we will learn classification of constraints.
A system of particles is said to be non-holonomic if it involves non-integrable differential equations of constraints. That means if a system involves non-integrable differential equations as a constraint, then it is called as non-holonomic system. Clearly, we can say that holonomic system of particles has integrable differential equations of constraint expressible in the form of equations. Further, holonomic constraints are classified as scleronomic, and rheonomic constraints. In that, the constraint relation which do not explicitly depends on time are called as scleronomic constraint. And the constraint which involve time explicitly are called as rheonomic constraint. That means the constraint which involves time explicitly are called as rheonomic, and the constraints which do not involve time explicitly is called as scleronomic. Now let us see some examples of scleronomic constraint. First example, the constraint involved in rigid body. in the motion of rigid body or in rigid body. Second, simple pendulum motion. Now let us write example of scleronomic, rheonomic. A bead moving along a circular wire of radius r with angular velocity omega is rheonomic constraint. Its constraint equation can be written as y equal to x tan omega t. This is the constraint equation of rheonomic constraint in this motion. Now, the constraint can be classified as unilateral and bilateral also. Let us see what is meant by bilateral constraint. Bilateral constraint. The constraint relation when the constraint relation are in the form of equation then such equations are called as bilateral constraint. That means in bilateral constraint there is equality sign. Now second, unilateral constraint. When the constraint relation are inequalities, then such type of constraint are called as unilateral constraint. That means in unilateral constraint there is greater than sign or less than sign. There is not equality sign. Equality sign is not there in unilateral constraint, and in bilateral constraint there is equality sign. Examples of bilateral constraint are motion of rigid body. Examples of bilateral motion are motion of rigid body, and examples of unilateral motion are unilateral constraint are motion of molecule in a gas cylinder or gas container. Now we can classify the constraint as a conservative and dissipative constraint also. Another type of classification, conservative. Conservative constraint. The forces of constraint do not do any work and total mechanical energy of the system is conserved while performing the motion. That means if the forces of constraint do not do any work and at the same time total mechanical energy of the system is conserved, then that type of motion is called as conservative motion, or then that type of constraint is called as conservative constraint. Example of conservative constraint are simple pendulum, with rigid support. If the simple pendulum has rigid support, then that type of motion is conservative motion. Then second type of motion is dissipative. Second type of constraint is dissipative constraint. If the forces of constraint do some work and the total mechanical energy is not conserved, then that type of constraint is called as dissipative constraint. The example of dissipative constraint is the constraint involved in the motion of pendulum with variable length. Thus, we can classify constraint in so many ways: conservative or dissipative, bilateral or unilateral, holonomic or non-holonomic, and holonomic constraint are further classified as scleronomic or rheonomic. This is the classification of constraint of a motion. Now let us discuss a question. Let us discuss a question with suitable example. Explain the statement constraint reduce the number of coordinates needed to specify the complete configuration of the system. We have to explain the statement. Constraint reduce the number of coordinates needed to specify the complete configuration of the system. For that purpose, we shall take example of a simple pendulum. Suppose this is the origin of a simple pendulum and it is tied. This is a bob and it moves from this position to this position. This is a simple pendulum. This is R, suppose, and angle of reflection is theta. Angle of motion is theta. We shall consider this example and show that the constraint reduces the coordinates needed to specify the complete configuration of the system. We shall write answer like this. Consider the motion of simple pendulum confined to move in vertical plane. Confined to move in a vertical plane. Or we would need only two coordinates. X, y, that is Cartesian coordinate, or r, theta, that are polar coordinates. With respect to origin O, to locate the position of ball in motion, bob in motion. To locate the position, we require two coordinates, either r theta or xy. The motion of bob is not free. We know this motion is not free. The motion of bob is not free, but it takes place under the constraint that the distance L suppose this is the distance L. Distance L of the bob from origin O, this is the bob, of the bob from origin O remains constant. The distance remains constant. From this constraint, we know that x minus 0 bracket square plus y minus 0 bracket square, this root is nothing but the length, and therefore from this we can conclude that x square plus y square equal to L square. But x square plus y square is nothing but r square. Therefore, r square equal to L square. From this we can conclude that r equal to L. And this shows that L is a fix. R equal to L is a fix. This shows that one coordinate, that is theta, in polar coordinate form is sufficient to describe the complete motion of bob. Thus, the number of coordinates are reduced from 2 to 1, and hence we can conclude that it reduces the number of coordinates from 2 to 1. The same thing can be explained, the same thing can be explained by taking other example. Consider second example. Consider a particle moving in a space. Consider a particle moving in a space. We know that we require 3 coordinates: x, y, z. The motion of a particle on spherical surface is a constraint motion. Is a constraint motion. As particle moves over the surface of the sphere, its distance from origin, that is center of the sphere, remains constant, and that is equal to radius of the sphere. If A is a radius of sphere, then x square plus y square plus z square equal to a square. Thus, if you consider it in spherical polar coordinate, then that is r theta phi. If we convert this into spherical polar coordinate, then r square equal to a square, this gives r equal to a constant. That means r will not change throughout the motion. Thus, to describe the motion, completely, we require completely on the surface of the sphere we require only theta and phi as independent coordinates. Thus, this shows that the constraint reduces the number of coordinates to specify number of coordinates needed to specify the complete motion of the particle.
Thank you. See you again in next video.